Hello, and welcome to the next video in my series on basic statistics. Now, a few notes before we get going. Number one, even though this slide says statistics, the concepts in this video are also applicable to finite mathematics. So you may see this video in a stats playlist or in a finite math playlist. Either way, it's applicable to both. Number two, these videos are geared towards individuals who are relatively new to stats or finite mathematics for that matter. However, I am going to assume that you know a little bit about random variables and discrete random variables, which are the precursors to this video. So if you're not sure about those concepts, go back and watch my previous videos on random variables and discrete random variables. And finally, if you're watching this video because you're struggling with a class, I want you to keep your head up. You're smart, you're talented, and any struggles you might be having right now, we can work through. And hopefully you find this video helpful. So all that being said, let's go ahead and dive right in. Now in this video, we're going to be extending our discussion on discrete random variables and random variables in general. In the last video, we talked about expected value, which is of course the mean or the average of a discrete random variable. So if you're in a course where you're using the term expected value, just keep in mind all that means. It's the mean or the average of a discrete random variable. So in this video, we're going to extend that idea into the variance and the standard deviation of a discrete random variable, which of course are just the next step when describing the data in a random variable following learning what the mean is or the expected value. So this is just the next logical step in talking about random variables and probabilities and things like that. So let's go ahead and get started. So, though the expected value tells us the mean of a random variable, its average, oftentimes we need to know the variability or how spread out the random variable is from that mean or its expected value. Same thing. So we're talking about the variability here, or how the data spreads out from the mean. Now we can use the variance and the standard deviation of a random variable to learn about how dispersed that data is relative to the mean, to the average. Now this information can be useful to calculate other statistics, to compare data sets, and inform other conclusions about our data. So in more advanced statistics, the variance of data, of the variance of different variables, is very important. In a large data set, you might have all kinds of different data. You may have categorical data, like male-female, or you might have continuous data like test scores or the temperature outside, but you need to find a way to use all those different types of variables in your overall model. And variance plays a very important role in the assumptions you can make about your data, or you have to make about your data in order to make those statistics work and things like that. So it's really important, and this is just another way of talking about variability in a discrete random variable. So here is the equation. Now don't freak out. It's going to be okay. You're thinking, oh my God, Greek letters and, there are more letters than numbers. It's supposed to be math. Well, in this case, it is true, but we're going to put numbers into the formula so you see exactly how this works. So let's take this apart step by step. Now if you notice in the middle we have equal signs. And what we're saying here is that all three of these expressions are saying the same thing. They're all equivalent. So over on the left-hand side, we have the variance of our random variable outcomes, which is the small x there. So remember, our discrete random variable will have a series of a finite number of outcomes in most cases, and each one of those outcomes has a probability associated with it, like a coin flip. A coin flip could be heads or tails, and the probability for heads is 0.5 or 50%, And for tails, it's also 0.5 and 50%. So that small x there just represents those probabilities. Now in the middle we have sigma squared, which is the common way of expressing variance. And then on the right-hand side, we sort of have this composite expression that tells us how we're actually going to calculate it. So let's start with the inside. In the orange there, you'll see we have our random variable outcome x minus the mean, which is mu. That's that u-looking character there on the right-hand side of our parentheses. So the random variable outcome minus the mean. Then we're going to square that difference. So we have our exponent there to square it. Then after we square that difference, we're going to multiply it by the probability of that outcome x, which is in the parentheses there. So this is merely the random variable probability minus the mean, square it, and then multiply that by the probability of that outcome. Now on the left-hand side there, sort of in the lightish yellow-orange color, you see our summation sign. And all that means is that we're going to do that for each outcome and then add them together. So let's walk through that one more time. Number one, we calculate the expected value of our random variable. And the mean is mu. So the expected value of a random variable and the mean are the same thing. We have to find that because we need that in our expression up there at the top. We have to have it. And I covered how to do that in my previous video. Now the second step, we take the random variable value, x, so whatever our outcome is, and then we subtract the expected value, or the mean. So I've color-coded it so you can see exactly how the steps correspond to the expression above. Now once we take the difference, we square the difference. Just that simple. So we square the difference there in the orange, in the parentheses. Now once we square the difference, we multiply it by the probability of the random variable, which is the p of x. And again, that's color-coded so you can see where it corresponds to our step. Now all we're doing there is we are weighting, applying weights to those what we call deviations, which are the squared deviations more specifically. So you can see it's just subtraction, multiplication, and the multiplication again. And of course I'm going to work through, I think in this video, 2 examples, and then several more in another video. So that's how we actually calculate it. Okay, now this slide, all this slide says is that if you take the square root of the variance, you get the standard deviation. That's it. So that's just a basic concept in statistics. The square root of the variance is the standard deviation. So once you calculate the variance above, take the square root, and you have your standard deviation. Okay, I start with a simple example, and that's a die roll. So if I roll a die many times and then average together my rolls, what should I expect for a mean? So I roll a die, write the number down. Roll the die again, write that number down. Roll the die again, write that number down. I do it many, many times. Then I average that together. What do I expect my mean to be? So as you know, we have 6 numbers on the die, 1 through 6. Now, we also know that each number is equally likely to occur. So on a fair die, each number has a probability of 1/6. And we'll show that here in the chart in a minute. Now what is the mean of 1, 2, 3, 4, 5, 6? Because remember, each number is equally likely to occur. And so if we roll the die many times, we're likely to get, 1/6 of the numbers will be a 1, 1/6 of those numbers will be a 4, etc. So what's the mean of 1, 2, 3, 4, 5, 6? Well, it's 3.5. And actually, if you look at the numbers on the die, especially up there in the top right, 1, 2, 3, 4, 5, 6, you'll see that 3.5 is actually in the middle. It's actually in the middle physically of 1, 2, 3, 4, 5, 6. So let's just talk briefly about the expected value. Again, I covered this in the previous video, but I'll do a quick walkthrough so you can see. On the left-hand side, in the red, we have each individual outcome on our die. So we have 1, 2, 3, 4, 5, 6. Those are our outcomes. In the middle column, in the green, we have the probability that corresponds with each outcome. So on a die roll, all the probabilities are the same. They are all 1/6. Now to find our expected value, we just take each outcome, so they're in the red, times its corresponding probability in the green, and then we get x times p of x in the right-hand column. So if we do that multiplication, we have all the numbers in the right-hand column, and then we add those up, and that is our expected value, or our mean, for this random variable. So that is 21 over 6, and of course 21 over 6 is 3.5. So just remember, the expected value is simply the mean of this random variable, the average. So over the long run, the expected mean, mu, for numerous rolls would be 3.5. So if I rolled this die 100 times, and I wrote the number down each time, I added up all those numbers and then divided by 100, I would expect a value of 3.5. Well, that takes us to the first step. We figured out the expected value, or the mean, which we need to have in order to figure out the variance. So down below, I've went ahead and included the expression for variance that we saw before. So as we build this process, you'll see exactly how it's put together. So here's a chart, and we're going to just do it step by step, real slowly, so you can see just how we do the calculations, because once you do one, you can do them all. They're all the same. So what you see here right now is merely what we figured out in the previous slide. We have our outcomes on the left, 1, 2, 3, 4, 5, 6. Our probabilities are all 1/6 because it's a fair die. Now in the blue, that's just the mean, or the expected value, which is actually the same for everything because there's only one mean, and that's 3.5. So we put that down the column. Now if you look to the fourth column, the first blank column, you see we have x, which is our random variable outcome, minus the mean. So this is just simple subtraction. So if you look down below, at the very bottom in the expression, I've actually highlighted what we're doing here. So it's kind of in a dark red. So this is the part of that expression we're actually doing. So if you look in the fourth column, we have the expected value. We have the outcome minus the mean, or the expected value. So 1 minus 3.5 is negative 2.5. 2 minus 3.5 is negative 1.5. So it's just the outcome minus the mean, or the expected value. And we do that for each outcome. Now in the next part, we just square that difference. Very simple. So I went ahead and included the 2 down there at the bottom, our exponent, to let you know that we've now included the squaring of the difference. So negative 2.5 squared is 6.25. Negative 1.5 squared is 2.25, etc. on down the column. So this is just the squared difference, or the squared deviation from the mean. Now in the final column, all we're doing is taking that squared difference and multiplying it by the probability there in the second column. Now for the die roll, they're all 1/6. That's because we're rolling a fair die. But we take the squared difference, so at the top we have 6.25 times 1/6, and as a fraction that is 25 over 24. And I know you can do fractions because you're brilliant. So down below that we have 2.25 times 1/6, 0.25 times 1/6, etc. So we go ahead and do that multiplication. Then of course our final step, because we have the summation sign, is to actually add all those fractions together. Now when we do that, we come up with 70 over 24, which reduces to 35 over 12, or we'll just sort of do some rounding and approximate that to be 2.92. And that is our variance for our die roll. It's just a set of very simple mathematical steps: subtraction, multiplication, and multiplication again, and then addition. That's it. So if we graph this die roll, remember it looked like this. So we have our outcomes along the bottom, 1, 2, 3, 4, 5, 6. The probability for each outcome is the exact same. That's why they're all the same height. And they're all about 0.17 or so in terms of probability. And of course, those probabilities have to add up to 1 by definition. So now remember, our expected value was 3.5. If we put that on our graph, it's right smack in the middle. That should make sense. Now our variance was 2.92. And remember, to find the standard deviation, we just take the square root of the variance. So our standard deviation is 1.71. We just take the square root of 2.92. Now along the bottom axis there, the x-axis, I have added stars that are one standard deviation from the mean, or from the expected value. So the star on the right is about 1.71 to the right of the expected value, the mean, the blue arrow. The star on the left is about 1.71 to the left of our mean, our expected value. So you can kind of see how the standard deviation is relative to the mean. Now just take a note, this is just a mental note, that about 4/6, which is 2/3, which is 67% of the probability of the outcomes are in between those two stars. So if we add up those 4 orange bars that are in between the stars, we have about 67% or 0.67. And that's actually an important concept, which we'll get to in other videos. But I just want to point that out, how the standard deviations relate to the mean and to the probabilities as a whole. Okay, one more example and then we're done. Now, in my previous video I used this example, and this is just the end of semester class satisfaction surveys or evaluations that students do in college and maybe even in high school. But I know in college I've done them as a student and as an instructor many times. So in this example we have 108 students in our class and they do an evaluation. And the overall question, the overall satisfaction question, has options of 1 through 5. 1 is very dissatisfied and 5 is very satisfied. And of course in the middle we have the gradations of dissatisfied, neutral, satisfied, sort of in the middle. So our possible outcomes are 1, 2, 3, 4, or 5. And of course the student can only select 1, and we're assuming they selected 1. Any student that marked more than 1 or did not mark it, we're not including in this experiment. We have 108 students that did the marking the proper way. And this is the data we had. Of course it's fictional, I made it up. So our outcomes are 1, 2, 3, 4, 5. Now the number of students for each was 5, 10, 11, 44, and 38. And of course we add all of that together, we have 108 students. Now to find our probability, the P of X for each outcome on the left, we just did some division. So it's just the count divided by the total number of students. And you can see that those 5 probabilities there are on the right. Now the question is, what is the average or the expected value for overall satisfaction in this class? And I did this in the previous video. Once we do the expected value calculations, which are very simple, it's just the outcome, which is the first column there on the left-hand side, multiplied by its probability. It's just a weighted average. That's all it is. Now when we did all that calculation, we come up with a expected value of 3.7, which is pretty good. That's pretty close to satisfied, which would have been a 4. So that's pretty good. Now our question for this video is, what is the variance? How spread out from that expected value, from that mean of 3.7 is our data? Is it going to be very spread out off to the ends? Is it going to be really clumped up and squished towards the mean in the middle? That's what we're going to find out. So I'm not going to go through step by step like I did in the die roll, but this is the exact same chart. So all we have is our outcome there in the red. Subtract our mean, which is 3.7, which is the fourth column. There's our subtraction. We square that difference, which is the fifth column, 7.29 on down. And then we take our squared difference and multiply it by our probability, which is over there in the green. So once we multiply the probability times the squared difference, we have sort of the proportion of our variance over there on the right. And then we add down, and we end up with a variance, a sigma squared, of 1.18. Now to find the standard deviation, we take the square root, and the square root of 1.18 is 1.09. So we have an expected value or a mean of 3.7, and we have a standard deviation, let's say, of about 1. So 3.7 plus 1 would be about 4.7, which is really good, or subtract 1 to be a 2.7, which is still pretty good. A 2.7 is almost neutral, and a 4.7 is almost very satisfied. That's really good. So if a graph of probabilities would look like this. Now, look at this graph. What does this say about our probabilities? Are they even sort of across our outcomes? Well, no. They are heavily skewed towards the right-hand side of our graph. So our mean, our expected value, is 3.7, which is about right there. Now, if you remember, if this were like a die where all the outcomes were equally likely, then where would our mean be? Well, it would be right at 3, because that's right in the middle. But here our probabilities are not like that. They're heavily skewed over towards the right. So our mean is going to be over to the right as well. Now remember, our variance was 1.18, and our standard deviation was about 1.09. Now down below I've placed stars again, where we're one standard deviation away from the mean on either direction. Now note that about 4/6 or 2/3 of our outcomes, the probabilities, are not between those two stars. So the only two orange bars we have are the satisfied and neutral. If you add those up, that's about 0.5. So why is that? Well, it's because our data is skewed way over to the right-hand side. So this distribution has sort of a lump over on the right-hand side. Therefore, a lot of our probability is over there. So I just want to show you how this is related to the standard deviation on a graph and to the mean, which is the expected value, and so forth. Okay, just review real quick and then we're done. So remember, the variance of the random variable outcomes, which is the little x, is the same as sigma squared, which is the same as the squared differences between the value and the mean times each probability. And if you want to clear that up, just go back and look at the charts. So we calculate the expected value, which is the mean, because we need it in our expression up there. Then we take the random variable value, subtract the mean, then we square it, and we multiply that by the probability of that outcome. And finally, we do that for each outcome and then add all that together, and then we have our variance. All right, well, that wraps up our discussion on discrete random variable variance, and for that matter, standard deviation. Again, this is just an extension of our video on expected value. The mean, or the expected value of really anything, whether it be a discrete random variable or a continuous one, does not tell us the whole story. That's why we do things like find the variance and the standard deviation. Now, I went over why that is extensively in another video, but the mean of a data set tells us very little, in my opinion. It does not tell us whether or not the data is spread out or it's very close to the mean. So in a previous video, I talked about how we could have two classes with exam scores that have the exact same mean, the exact same average class score, but the variance and standard deviation were much different. One was much closer to the mean, one was much more spread out. So the class with the more spread out scores had more extremes. It had more students that did very well, but it also had more students that did very poorly, even though the average for the class was the exact same as the first class. So this is just bringing that into the idea of discrete random variables so we can begin to compare data sets, to make conclusions about our data, and things of that nature. All right. So, all that being said, let's go ahead and wrap up. Thank you again for watching, and I look forward to seeing you again next time.